solids, what are the typical units of density for a solid? Mass over volume, grams per milliliter for a liquid, but for a solid it's typically grams per cubic centimeter. So we're going to convert the radius into centimeters in order to get those units. So, how do we go from picometers to centimeters? So going way back from week 1, so you might remember that centimeters was 10 to the minus second, and picometers is 10 to the minus 12. And then you flip the units, or flip the powers of 10. I just love it when the basics come back, you know. It's like, oh, this is why we're studying metric units. So if you convert one edge length here, it's 3.34 times 10 to the minus 8 centimeters for an edge length. So one edge of the cube this up. All right. There we go. I finally got a cube on the board. Okay, so this edge length here is that. Okay, one edge length of the cube. So what would be the volume of the cube then? All right, volume of the unit cell. How do we get the volume? How did you measure the, in Chem 107, how did you measure the volume of an object, a solid object typically? Yeah, length times width times height. So we're going to multiply this 3 times, right, to get the cube. Right, so we're going to say edge length cubed is going to be equal to 3.34 times 10 to the minus 8 cubed. So that would give us 3.73 times 10 to the minus 23 cubic centimeters. All right, so we have the volume of the cube. So to get density, we have our volume now, right? We just need to get the mass of the atoms that occupy that cell so that we can get our density. So one simple cubic unit cell contains blank number of atoms. Do you remember? One, right? One atom, right? Right, one whole atom. And we're assuming that all these locations at the corners are polonium atoms, right? So it's one total polonium atom. So the mass of the unit cell is equal to one atom. And how do we get from atoms of an element to grams of an element? So we have, right, we have 6.022 times 10 to the 23rd atoms for every 1 mole of PO. And how would we get from moles back to grams? Molar mass, right? So polonium has a molar mass of 209 grams per 1 mole of PO. Do you remember that flow chart thing I mentioned? It's going back to that, right? This is like the wax on wax, like, oh, got that one. Oh, from like 15 weeks ago. Oh, we're using it. Okay, so we can get our mass of a unit cell from that, and we end up getting 3.47 times 10 to the minus 22nd grams of polonium. So we have our volume, and we have our mass. Find the density. Right, so it says density is equal to mass over volume so 3.73 times 10 to the minus 23, oops, excuse me, that goes at the bottom. 3.73 times 10 to the minus 23rd cubic centimeters, and it'll take us 3.47 to the minus 22nd grams, and we will get a density of 9.30 gram per cubic centimeter. And if you look at the density of polonium, you would probably find a value pretty close to that. So you can get the volume from the edge length, you can get the mass of the knowledge of how many atoms are in the unit cell, and go from there. So that's the density. The question also asks us for what's the packing efficiency. So we know what V cell is, right? But we need to know what volume that the atoms take up. So we know that the volume of a sphere is 4/3 pi r cubed. Right, that's the volume of a sphere. So the radius was given to us as was it 3.34 to the minus 8th, right? No, that's the edge length. Okay. It's just going to be 167 picometers converted to centimeters, and we got to cube this. All right, so plugging that in, the volume of a single cell so this is the volume of 1 PO atom. What if I had more than one atom in the unit cell? I'd have to take that into account as well. Like if there were 2 atoms or 4 atoms in the unit cell, I'd have to multiply this by 4 to get the volume of the atoms. But in this case, it's just 1 atom. Okay, so to get the packing efficiency, percent packing efficiency would be the atoms divided by the volume of the cell itself times 100 So we have 1.95 times 10 to the minus 23rd cubic centimeter. What's our volume of our cell? 8.73 to the minus 23rd. And multiplying that ratio by 100 would give us 52.3% packing efficiency. Times 100, this whole thing. Is this close to the ideal packing efficiency for a simple cubic size? The answer is yes. Okay. So simple cubics have packing efficiencies of around 50%. Alright, so looks like we'll have to just continue this next time.